All right, I'm going to show you guys Lagrange Error Bound, and just the name Lagrange. If you see that name, it's usually a high-end thing. Rene Lagrange would just solve things that a lot of people didn't tackle. So it's just some high-end stuff. So if I quote my son, he would say like, "Hey, if it's got Lagrange's name on it, it's high-end." So there's something you'll learn in the future, maybe called Lagrange multipliers and stuff. But here's where he discovered error bound. When you approximate a value, you're approximating, so you have an error. So when we have alternating series, we learned an alternating series bound back when we learned earlier in chapter 9, where we learned the alternating series test. And at the end, you'll see I showed you guys alternating series bound. So if you have an alternating series, that was one formula. This one's kind of similar, but it works for other series. It doesn't have to be an alternating series. And so you'll see it looks very similar to that alternating series one. And what this is saying is, when you see these symbols, it looks like gibberish until you learn how to decipher them. The absolute value means distance, or the difference between the actual function and our Taylor series polynomial. So Taylor series is an approximation, so they're saying the difference between the actual answer and the answer you got, your approximation, is less than or equal to some value. So we actually can solve what the error is. So, the remainder, that's why it's R, the remainder, what's left over, is less than or equal to, now here's where this formula comes in, the next term. Now, it's the plus one term. And that's where first time I read, I was a little confused. If the series is going 2, 4, and you go like, oh, the next one will be 6, the next term will be 5 in this one. You actually do plus 1. So even if you're jumping by like 7s, 7, 14, 21, then you would check 22. Okay? So it's the plus 1 term. So that's what they're saying. So you plug in the plus 1 term. Now what this is you would actually take the plus 1 derivative. So if you have a 4th degree Taylor series, you would take the 5th derivative of the equation. And they want the maximum value of that derivative. Well, it was very confusing for me. Like, I was looking in textbooks going, how do you find the maximum of a derivative? What's the maximum? Now, every textbook I look at shows trig. Well, trig's pretty easy because sine and cosine have a max of 1. They just go between 1 and minus 1. So those are easy to do every time, and that's kind of the one they show, which I'm going to show you right now, and then I'll show you how AP asks it, okay? So none of the textbooks are willing to tackle or have tackled, like, hey, what about a different kind of problem? So I'm trying to find one, but here's how it goes. So we know cosine is this 4th degree. So this is cosine, it's known. Now that's a 4th degree Taylor series. And we can use it to approximate a value. So if I plug in 0.1 into it, so I plug in 0.1 and I get 0.995 in this long decimal. Now the actual value looks very similar. If you compare those two, it's accurate to about 8 decimal places. That's pretty good. So, and we only did a 4th degree Taylor, but the error is what's the most the error will be. So the error itself is what you're saying is the difference between actual value of cosine and our 4th degree Taylor polynomial. So that's what we're finding the error of, is less than or equal to what? Well, it's less than or equal to the next term. Well, the next term will be x to the 5th over 5 factorial. You just add 1. But there's going to be a multiplier in front. Now, we're going to be plugging in 0.1 into this in just a second because we're checking this is all at 0.1. What's the error at 0.1? So I'll be plugging in for x 0.1. But the multiplier is, what's the maximum the 5th derivative could be? Well, what's the 5th derivative of cosine? Well, it turns out to be negative sine. So what's the maximum negative sine would be? Well, 1. All the trig functions, sine and cosine, the max, whether positive or negative, is 1. So you would multiply by 1. So I thought, okay, what about another equation? What would the max be? And so we can plug in 0.1 to the 5th power over 5 factorial, and that's what our error is going to be. So we know it's less than that value. So it's going to be less than or equal to, I did it earlier, I got like 7 zeros. And that's the error that we're saying we know it's going to be smaller than that, and actually the actual error, if you see, you know, is better than that value. So that's how we do Lagrange, and all we're doing is seeing how accurate we are. But look how accurate we are. I mean, we like to round to 3 decimal places, and we could round to 8 and still be accurate. So that's a pretty accurate answer. As you can see, they're exactly the same at 3 decimals. So the error isn't very big when you go, the further you go with Taylor series, the more accurate you are, of course, right? And 0.1 is pretty close to 0. So the further you get away from 0, the less accurate. So if I check 0.2, 0.3, we might have seen a little more of a gap, right? Okay, so here's how AP asks it. So they're giving us all the key things we need to write a Taylor series. Should be easy. They want us to write a second degree Taylor series. So a second degree Taylor series. Remember, we're just going to use those up to the second derivative. Those are my multipliers, 2, 5, and 7. So we got 2. My next term, 5 and 7. So remember how to write it. The center is 1 because we're checking at 1. So that's our second degree Taylor series, okay? They want me to approximate 1.1. So they want me to plug in 1.1. Now, I don't know what the original is, but I can approximate 1.1. So I plug in 1.1 into that. It turned out I already did it. It was 2.535. So that's our approximate answer for 1.1. Well, Lagrange could say, well, how close we are. We don't know what the original problem looks like, but we can actually find the error. How close is this error? So the actual error would be the difference between the actual function and our second degree is less than or equal to, and we got to do the next term. So that's why they gave me this extra guy. They gave me the third derivative, but only asked me to write a second degree. So what AP will do is they'll come up one short, and then they'll go, hey, what's my error? And you're like, well, that turns out to be the value that you're multiplying by. So I always thought, like, how do I find this value? AP always just gives it to you. So we're like, okay, so you're just going to say it's 12 times. And we're plugging in 1.1 into the next term. So the next term would be cubic. We stopped at 2. So it'll be 1.1 minus 1 cubed over 3 factorial. All right. And that's kind of what the third term is. Or the error, excuse me, not third term. So the error using the third term. And so we get 0.002. If you do the math there, 12 divided by 3 factorial 6, you get 2 times 0.1 cubed. 0.1 cubed is 0.0001, and multiply 2. So we know we're that close. So the actual value could be like somewhere between 2.535 and 2.537 if we were going forward, or if we were going backwards between 2.535 or 533. So 0.2 in each direction. So that's how you find the error. That's how Lagrange asks us to do it. They'll ask different ways. We'll learn in class, and we'll see some different ways they give you that multiplier. That, to me, was the hardest part, was how do I come up with this? And AP usually says, hey, the third derivative has that derivative of 12. And we're like, okay, I can use that. Okay? So that's Lagrange Error Bound. You just plug into, again, the next term. Okay? So if we ended in 2, you would plug in 3. If we ended in 28, you plug in the 29th, okay? All right, so that's Lagrange Error Bound at a pretty simplified level.